Introduction to AC theory. Okay, so what we're going to have a look at in tonight's session is the generation of a sinusoidal waveform. How does that come about from a basic generator? The properties of a sinusoidal waveform. How a sinusoid bit can be expressed in form of an equation. So the standard form of the equation for a sine wave, and calculations involving instantaneous values of sinusoids. Yeah. So that's where we go on, what we're going to cover tonight. So, generator in its most basic form. If we have two permanent magnet poles, as shown there, pretty much primary school, secondary school science, you'd know that there's a magnetic field north to south between the two. Yeah. And if we rotate, so what we've got here is a single copper or other conductor winding in a loop between those two magnets. Yeah. And if we rotate that at an angular velocity omega, okay, as the copper conductor cuts across these lots of magnetic force, it induces a current in the coil. Yep. So that's the basic operation of a generator, and we'll do that so long as there is relative motion between the two, between the conductor and the field. Yeah. At the point it is now, yeah, effectively the coil is moving in the same direction as the field. So at that point there would be no voltage. The point where the highest voltage is here, where it's cutting across at the south pole and the north pole, because that's at right angles then. So that's where you'd get your peak. Okay? Now, if we move on from that a little bit and look at the stages as this coil goes around one complete revolution. As I said, at that horizontal position, no voltage generated. At the halfway between there and the North Pole, some voltage generated. When that conductor's at North Pole, maximum voltage generated. As we move around to the opposite position to here, we start to come down again. There we've gone a half a revolution, we're back to zero being generated, and the same in the other half cycle, but we've got a different conductor near the North Pole to what we had, so that effectively the current's flowing in the opposite direction. So we get these data points from each of those positions. Yeah, and if you join up the dots, you've got a sine wave. It's got a positive peak here and a negative peak there. Yeah. There's a period of time, can be in seconds, or it can be an angle in degrees or radians that we can express on that axis, because it's gone through one full cycle, 360 degrees, or 2 pi radians. Yeah. So mixture of terms, depending on the type of problem we're looking at, we're going to come across a mixture of terms expressing that axis. Okay. But always on this axis, that will be the current instantaneous amplitude that you'd get from the y-axis. Yep. All right. on this page, which ones of those, A to F, are would give an AC current if you connected them? So their voltages. Which ones would cause an AC current to flow? So you think that one's AC? Yeah. And yeah, G is the expression of a sinusoid. Not B, not A. Why not B and A? Oh, they are DC. And they're DC because they don't cross zero. Remember, it's alternating current is what the term means. Yeah. So it's suggesting that the current alternates between going left to right, right to left. Alternates one direction to the other direction. So that implies that the voltage causing it must be crossing zero. And in those two it isn't. They're changing, so the current will be going up and down, but because it's not crossing zero, it's not going to change direction. Alright? The terms that are on here, I think I got better on the next pages because I'll draw them in bigger diagrams. Okay? Because AC voltage causes alternating current, i.e. effectively in a circuit where I'm going to draw the red half positive, that half is red, the other half, we get a current flow, draw that in black, through the circuit where in the red half cycle current will be going in that direction, and in the green half cycle current will be travelling back in that direction. Yeah. And on our mains electricity, that happens, changes direction 50 times a second. Yep. Okay, so significant terms about the AC sine wave. First of all, the period of a sine wave. The period of a sine wave is defined as the time taken for one complete cycle in seconds. Yeah. So one complete cycle is about the generator, if a single pole generator, rotating 360 degrees or 2 pi radians, but the period of that waveform is how long that revolution takes, basically. Yeah. Related to the period is the frequency. So the frequency of the waveform is how many cycles per second. Yeah. So if the period is 10 seconds, yeah. Sorry, hang on. If the period is half a second, then the frequency would be 2 hertz, 2 cycles per second. Yeah. So frequency and period are reciprocals of each other. You can get the frequency by 1 over the period, and you can get the period by 1 over the frequency. Alright? Yep. Okay with that so far? Good. Now, peak and peak-to-peak values of a sine wave. Diagram below shows the peak, and the peak-to-peak value is AC waveform. If the waveform is centered around 0, then the peak is the distance between 0 and the maximum value, positive value of that waveform. There's also a negative peak. Peak to peak really has no scientific value whatsoever, but when you measure a waveform on an oscilloscope, it's much easier to measure peak to peak and half it to get the peak value. Sometimes in hi-fi specifications you'll see things specified peak to peak. Really, that's not a valid specification because the waveform it's never supplying 200 volts. It's only ever supplying a maximum of 100 there. Yep. All right. So their terms, you can if you want to determine what the peak is, you know what the peak to peak is, you just divide it by 2. Yep. So peak value is peak to peak value over 2. Root mean square. The root mean square, RMS value, is an important value for AC waveforms. Yeah, I'm going to stick to considering a sine wave, but the diagram below shows the peak-to-peak values of an AC waveform. Right. The RMS value of AC waveform is the value that would dissipate the same power to a given load as the equivalent DC value. Yeah. So if we take our wonderful AC mains in the UK, 230 volts, that nominal voltage, the stated voltage of that, is the RMS value. It actually peaks at 300 and some odd, we'll calculate it in a minute, volts. Yeah, it's a straight line value, doesn't go up and down. What we're saying is this 100 volt AC sine wave would deliver the same power to the same 10 ohm resistor as a 70.7 volt DC power supply. Yeah, it's like a sort of an average. It isn't the exact average. It's a special root of the mean square. Okay, but that's what it does. So, and this is only for the sine wave function. If we were talking about a square wave or triangular, the maths would be completely different. Right? We're only interested in sine wave. For a sine wave, the RMS value is 0.707 times the peak value. That 0.707 is an approximation. If you want it precisely, 1/√2. Yeah. So if you use that in your calculator, that's exact. 0.707 is a close enough approximation for most things. Yeah. So if you have the peak value, you can find the peak value from the RMS value divided by 0.707. So do 230 divided by 0.707. Off the dot there anyway. 325 volts. Yeah. So that AC mains peaks at 325. 400 volt between phases on a three-phase system peaks at 566. One particular thing where that has implications is if you're using capacitors in AC main circuits, their working voltage needs to cater for the peak value, not the RMS stated value. So it's no good going in your stores and saying, oh, I got this capacitor, that's 250 volt working, I can put that on that AC mains job. because that will destroy it. You need one of at least 325 volts working. All right. Now, when it comes to taking measurements, I'll put a note there. If the waveform is a different shape, e.g. triangular, then this calculation will be very different. Okay. Inexpensive multimeters, and I'm talking about your digital meter, right, will give a correct, they're designed, they've got a conversion thing in them, so they convert, so they give an RMS value for a proper sine wave. Yeah, but if you put them onto a triangular wave, they won't give you a true reading. You have to pay a lot more money for a true RMS meter, which will then give you a true RMS reading for any shape waveform. All right, so it's just worth knowing that meters read RMS. Yeah. Okay. What the cheap ones do is read average, which is about 0.636 of peak, I think, and then convert between that. So use internal conversion to convert between that and the 0.707 value of a sine wave. Yeah. So if you're not doing a sine wave, that conversion factor is incorrect and it gives you incorrect read. Okay. Moving on from that, we have angular frequency. Angular frequency of a sine wave is the number of radians turned in 1 second. Yeah. So angular frequency is designated by the Greek letter, what looks like a W, but a lowercase omega, and it's equal to 2 pi times the frequency. Remember what the frequency is. It's how many times it goes round in 1 second. Yeah. Omega is how many radians it travels in 1 second. So if we say we know it goes round 2 pi radians for every complete rotation, so if we multiply that by the frequency, we get the angular frequency as how many radians it travels in 1 second. Yeah. And so that's an important quantity in the formula, the full expression for a sine wave. Usually you express the frequency in omega form. Yep. All right. So, moving on from that, we need to consider the instantaneous values of a sinusoid. As the conductor moves around in this generator anti-clockwise, it generates voltages up to the peak and down. Okay, these blue arrows all represent instantaneous values. At a point in time. Yeah. So it's what the voltage is at a given time in seconds. Instantaneous values are always designated by a lowercase letter. For example, V open brackets T. What sine is, this is the voltage at time T is. And you need to make sure when you write up your answers to questions that you make sure that you distinguish between instantaneous values, lowercase, make it really obvious that your lowercase is small and your peak value, which is represented by the capital V or the capital I or the capital P if that's power. Yeah. So what we can do, any instantaneous value of a sine wave where V, little v is equal to 0, at time t is equal to 0 can be found using the formula V at time t is equal to capital VP, that's the peak value of that waveform, or the amplitude, yeah, multiplied by the sine of omega t, omega being the angular frequency. So that's the standard form of sine wave at 0 degrees or 0 radians, i.e. no phase shift. Yeah. So if we take that little v is equal to Vp sine omega t. That is the amplitude. Yep. That is angular. Yeah. You might also see in some books that you get a VP sine of an angle in degrees or radians, because that's talking about, I might do that when that's kind of a mechanical or a more scientific thing. But when that's electrical, you're usually working in omega form radians per second. Alright? Yeah? That's not amplitude, that's amplitude. Yeah, alright with that so far? Good. Yeah, okay.